Hello again, PCS 622. So I want to do, in this pre-lecture, I want to go back to a topic which we haven't touched on for a while, which is the Fourier series. So we've been spending a lot of time solving PDEs and using Fourier series to solve those PDEs, partial differential equations. But I want to sort of switch gears now and build up towards the end of the semester. We're kind of working our way towards this thing called the Fourier transform. And in order to get there, we need to go back to Fourier series, but try to think about them in terms of complex variables. We're going to return to Fourier series, but think about it in terms of complex variables. So let's get started with that. All right, so this semester we started with the Fourier series, what we call Fourier trigonometric series. So what I've written here is just our review of the Fourier series, trigonometric series using cosines and sines. Remember, this was applicable for a period t, or let's just say the period is equal to 2L. And then we have our formula here for the Fourier series, and we have the formulas here to calculate those Fourier coefficients. Now, you remember from last semester we spent a lot of time talking about how complex exponentials are sort of easier to deal with than trig functions. And generally, why is that? And the reason for that is usually because of derivatives. If you take the derivative of e to the ix, you just end up with, I times e to the ix. So I just multiply the function by a simple thing. But if I take the derivative with respect to x of cosine of nx, I get a different function, which is a sine, right? Minus sine of nx times n. So the problem with sines and cosines is that when you take a derivative, it kind of mixes the sines and the cosines up. But if you take a derivative of a complex exponential, you just get the same complex exponential back again. So what we want to do is, let's try to develop Fourier series using complex exponentials. Instead of sine and cosine. And of course the connection there is going to be made by Euler's formula. E to the I theta is cosine theta plus I sine theta, right? And you can, if I write e to the minus I theta, I get cosine theta minus I sine theta. I just change the I to minus I. And then if you add these two together, you get, hopefully this seems familiar from last semester, cosine theta is 1/2 e to the I theta plus e to the minus I theta. And sine of theta is 1/2I e to the I theta minus e to the minus I theta. So what I'm going to do is I'm going to go back to the Fourier series and I'm going to remove the sine and the cosine using Euler's formula here. Okay. All right. So to save myself writing, I'm going to let theta equal to pi x over L. And then I'm going to rewrite my Fourier series. My Fourier series will look like this. F of x is equal to a0 over 2 plus sum n equals 1 to infinity, an, cosine of n theta plus bn of sine of n theta. So I'm just saving myself some writing by defining that theta there. Now what I'm going to do is substitute in for cosine of n theta and sine n theta the formulas here coming from Euler's formula. All right, so let's do that. So here we're going to have a0 over 2 plus sum n equals 1 to infinity an, and now I'm going to substitute in 1/2 e to the I n theta plus e to the minus I n theta. Okay, plus bn over 2i times, well, let me just make it more explicit, bn times 1 over 2i e to the I n theta minus e to the minus I n theta. Okay, so all I did is I just rewrote my Fourier series. This is cosine of n theta, and this is sine of n theta. Okay, so I used Euler's formula to rewrite my Fourier series. Okay, now 1 over I is minus I. So let me change this minus to minus and bring the I outside up to the top there. Okay, so I'll put here I over 2. Okay. All right, let's group the terms a little bit. So a0 over 2, I'm going to group everything together which has an e to the I n theta. So what do I have for e to the I n theta? I've got this term and I've got this term. So I'm going to have an over 2 minus I bn over 2. Okay. And then I'm going to group together the terms which have e to the minus I n theta. So I'll have plus e to the minus I n theta. And which terms multiply e to the minus I n theta? I've got another an over 2. That's the first term underlined in blue. And then the second term underlined in blue is plus I bn over 2. Like that. Okay. So all I did is just rearrange the terms. I put everything multiplying e to the I n theta together and everything multiplying e to the minus I n theta together. Now this is a sum. Like this sum is applicable to both of those terms. So I want to make it explicit, and I'm going to break this into two sums. Okay. So what I'm going to do is let me just take this guy and move it over a little bit and just make it clear that this is also summed n equals 1 to infinity. Okay. So I just had a summation over two terms, so I'm just writing it explicitly there. Okay, now I'm going to play with this first sum. And I'm going to do something called reindexing. Maybe you know how to reindex a sum, I don't know. So for example, what if I wrote the sum of from n equals 1 up to 3 of 1 over n? Okay, what is this? This is 1 plus 1/2 plus 1/3, right? But I could also write this as the sum n equals 0 to 2 of 1 over n plus 1, right? That would also be 1 plus 1/2 plus 1/3, right? It's kind of like a U substitution. It's basically the idea. Basically, I'm changing this variable into something else, and then to compensate for it, I need to do something to the limits here, right? So as long as I change the variable and the limits in a consistent way, I end up with the same summation. Okay, this is called reindexing the sum. What I'm going to do to reindex this sum is I'm going to change n to minus n. Okay. So that was just an example. So I'm going to change n into minus n. Here's another simple example. What if sum n equals 1 to 3, 1 over n? We already know that's 1 plus 1/2 plus 1/3. What if I change n to minus n? So I could have this 1 over minus n, right? But then I have to have n going from minus 3 up to minus 1. The first term, n is equal to minus 3. That's 1 over minus a minus 3, plus 1 over minus a minus 2, plus 1 over minus a minus 1, which is again 1 plus 1/2 plus 1/3. Okay. So in other words, again, like a u substitution, if I let x equal to minus u, so then this becomes negative, but then I have to change the limits of integration in order to reflect that change. And so if I change n to minus n, but also change the limits, I'm not going to do anything to the sum. So we're going to do this same thing on the summation above. So what am I going to have? a0 over 2 plus the sum. Now n is equal to minus infinity to minus 1. Okay? So just like before, I had to change the limits, and then everywhere inside the summation, I change n to minus n. Minus I n theta, a minus n over 2 minus, minus I, bn, b's minus n over 2. Okay? So what I did is I changed everywhere in here, I changed n to minus n, and then I also changed the limits here, and hopefully you can verify just by writing out a few terms that these are the same terms as before. I'm going to get the same sum. I didn't change the value of the sum, I'm just writing it a different way. Okay. Now, almost there. We have to think about what does it mean for there to be a negative index on these ANs and BNs. Okay. So let's take a side note here. Remember these formulas for the coefficients. AN is 1 over L minus L to L. F of x cosine of n pi x over L dx, right? But a sub minus n, so what if I put a negative number in for L, or sorry, in for n? Cosine, I would have cosine of minus n pi x over L. The cosine of minus n pi x over L is equal to the cosine of n pi x over L, because cosine is an even function. Okay. So that means a minus n is equal to a sub n. Okay. So the upshot here is that a sub minus n is equal to a sub n, okay, because cosine was even. What happens with the bn, b sub minus n? It's 1 over L minus L to L, f of x, sine n pi x over L, sorry, minus n pi x over L, dx. But sine is odd, so this is minus sine of n pi x over L. It's odd, right? So there's an extra minus sign that shows up here. So this is minus b sub n. Okay. So what we learned out of this is that b sub minus n is minus b sub n. And let me take this whole thing and bring it down below. So this is my f of x. Okay, so I've just written down here the expression for the Fourier series. Here I just recopied it after I did the indexing. And now we're going to use the things highlighted in yellow there, that a of minus n is equal to an, and b of minus n is minus bn. So I'm going to change in this first sum here, I'll just change a sub minus n is equal to a sub n, and b sub minus n is equal to minus b sub n, so I can make that a plus. Okay. Now take a look at these two terms. This term here is exactly the same as this term here. The only difference between these two is the bounds on the sum. So the first term is over the negative integers, and the second term is over the positive integers. So I can combine those into one term, a0 over 2, plus sum n equals minus infinity up to infinity, with a note that I'm ignoring the n equals 0 term, because see, this one goes from minus infinity to minus 1. The second one goes from 1 to infinity. There's no n0 term in there. And then I have this, e to the minus I n theta, an over 2, plus I bn over 2. There's one term missing, which is that the n equals 0 term. But what is the missing term? Is this one. E to the, when n equals to 0, right? E to the minus I times 0 times theta, a0 over 2 plus I b0 over 2. But hopefully you remember there's no b0. This is 0. And this is 1. So the missing term is a0 over 2. And the amazing thing is that that is exactly this term that we have out in front there. So I can get rid of this a0 over 2 and just bring it inside the summation n equals minus infinity to infinity. Just this, e to the minus I n theta, an over 2 plus I bn over 2. This is f of x. Okay? So I've written it all in just one single summation there. These are a bunch of constants. They're complex constants because there's an I sitting there. So the an and the bn are real numbers. So we usually call these Cn. So Cn is defined to be an plus I bn over 2. Okay? What exactly is the Cn? Well, let's just write out what it is. Cn is an plus I bn over 2. And let's write in the formula. So 1 over 2. An is minus L to L, 1 over L, f of x, cosine n pi x over L dx, and then plus I times bn, minus L to L, f of x, sine n pi x over L dx. So this here is an, and this here is I times bn. But notice that you can simplify this. So let me pull out the 2L. Combine those integrals into one. F of x cosine n pi x over L plus I sine n pi x over L dx. But this whole thing is Euler's formula, e to the I n pi x over L. So we have a simple formula for Cn, 1 over 2L minus L to L, f of x, e to the I n pi x over L dx. Let me summarize what we've done so far. So here's the summary. We have the complex Fourier series, which is here. F of x is equal to sum over all integers, both negative and positive, minus infinity to infinity, Cn e to the minus I n pi x over L. And those Fourier coefficients are found from this integral, 1 over 2L minus L to L, f of x, e to the I n pi x over L. So we have here a complex Fourier series And these are my complex Fourier coefficients. Look at how nice this looks. Just one single formula for the coefficients. Everything is totally symmetric from n equals minus infinity to infinity. I don't have a separate sort of a0 over 2 term sitting out there. I don't have to have two different integrals for the an's and the bn's. So this formula is really, really nice. It's a nice way of writing the Fourier series. You know, what we haven't really done anything other than rewrite the Fourier series that we had using Euler's formula and a few mathematical tricks. Okay? But the result you get is very nice and compact and symmetric. And we're going to use this form for the Fourier series for the rest of the semester. So we're going to work only in terms of complex Fourier series for the rest of the semester and not trigonometric functions. So in class, we'll start working on some examples with this to get you some practice with it and kind of get the brains working again with Fourier series. And then eventually we'll work our way towards Fourier transform. I hope you've enjoyed this pre-lecture, and I'll see you all in class.